Today we are going to talk about generative models, about variational autoencoder and GANs. First, let's discuss what are generative models and what is different from discriminative models that we were talked before. Okay, let's discuss our problem. We have a data set x1, x2, xn. This could be text, images, or whatever we want. Before, we discussed tasks where for each sample, we labeled it. For example, like a classification class, segmentation, in fact, or object detection is very similar to this. We can derive the formulation into a discriminative manner. So the main idea was to label some samples. These called discriminative tasks. But today we would talk about generative tasks, where our purpose not to label existing samples, but to generate new ones from the same distribution. Let's say some words about what is distribution. So we have some objects. Let's take, I don't know, digits from 0 to 9. Yeah, 9 objects. And this is, for example, our data set. And we have distribution. This means that each object is not uniformly distributed. For example, we can take 0 with 0.5 probability, and others, for example, 1 with 0.2 probability, 2 with 0.3 probability, and others with 0 probability. This means that if we will take a random element, we will take these three elements with these probabilities, and others with 0 probability, so we wouldn't take them. In fact, what are probabilities? In fact, for each element, we match a number, a probability with the property that each probability is from 0 to 1, and sum of all probabilities is 1. Okay. We also can match probabilities not only for discrete objects, but also for non-discrete objects. Like, let's take numbers from 0 to 1 and match. I would call this probability, but in fact, it is not correct. But let's say the strict explanation is, let's, for example, if we have numbers, all numbers from minus infinity to plus infinity, and let's say that find the probability that random number is less than some constant, I don't know, t. Yeah. And we will call this function a distribution function, f of x. This means that the value of this function means that random number, the probability of a random number to be less than t. Oh, sorry, not f of x, but f from t. So if we take t, we know that a random number will be here with probability f of t. Okay. And we have a density function. It's a derivative of f of t. It's called density function. Like, I don't know. Yeah, here x is a random variable from our distribution. What means density function? First of all, we can say, for example, what is the probability to take an object from 0 to 1? Using our distribution function, we can say something like f of 1 minus f of 0. Yeah, this means because f of 1 probability to be less than 1, f of 0 probability to be less than 0. And in terms of our derivation of our density function, it's we can count integral from 0 to 1 of this derivation, and it will be f of 1 minus f of 0. Yeah, so this equals to, it's a simple calculus because p is derivation. Moment. From 0 to 1. So it's some formal ideas. It's some formal formulas, but let's talk about ideas. Now we have a data set. It's like our objects, and we want to say that we have a distribution on it. For example, if we talk about text, some words are more often than other words. You can see them more times. For example, you can see in English, you can see and more times than table, I suppose. Yeah, so it's not fair to say that each element is equal. Some elements are, some elements are more important, for example. The same we can say about images and other modalities. So now we have objects. Usually we encode objects with some, I don't know, R in degree n, because images, we can encode images like this, we can encode text like this with embeddings. And we can say that our objects are in degree n. And for simplicity, let's say that we have n equals to 1. So we have some objects, yeah, and we have distribution on it. And next we will say that we have density function on it, and this is our data. Not only samples, but also probabilities, density function, so also distribution on this data. Okay. Now talking about generative task. Now we want to generate samples and also generate samples considering our distribution. So if we want to generate words, for example, we more likely want to generate and. It depends, of course, on our data set, but some objects we will want to generate more often than others, for example. Why it is important? Because, for example, when we generate images, if we have samples Rn, yeah, they can be really strange images, some random images, random pixels. But we want to generate real images with dogs, with cats, with people. Yeah, so probability of real images should be higher than probability of some trash like random pixels or fully white image. Yeah, that's why it's important to have distribution. And here you can see that we have data set from cats and dogs, and we have distribution. And here red means high density. yeah, and white low density. In fact, in ideal world, it should be 0, but because we work with neural networks, let's say that it's usually probabilities here are very close to 0. And probabilities in quantum images should be close to 1. Something like this. Okay. So talking about probabilities, usually we have discriminative task where we have sample X, for example, our image, and want to predict sample. We want to predict class Y. What does this formula mean? P is density function on labels, but considered on image X. This means that we have image X, and we should obtain distribution on labels. So usually we do the same. Our neural network predicts pseudo probabilities, and we choose the maximum, the argmax from this vector, and obtain index of label. So in fact, we predict distribution on our labels considered on image. Yeah, because in input we have image X or text or something else. For generative model, we want to sample from distribution P of X, as we discussed before. Okay, let's go on. This is the difference between generative and discriminative models or tasks. Okay, the first question is where to find randomness, because as input, we don't have anything because we want to generate from distribution. And in input, we don't have anything, and we should obtain an image, for example, from this distribution. And next time we will run, in most of our models will output the same image because our models are deterministic. Where to find randomness? Well, we will take some some easy distributions on easy data. For example, Gaussian noise. What is it? We have distribution on real numbers. Let's see on the right. This is a density function, f of x. And it looks like here. You can see graphics. Mu is mean of x. In fact, what is the mean of distribution? If we have distribution, we can count expectation of random variable from this distribution. And speaking in terms of idea, it is like mean value of this random variable. For example, if we play a game and with probability 0.5, we will obtain, I don't know, $1. With probability 0 and 1, obtain $100. And with probability 0 and 4, obtain $2. How much money we will obtain at the end, let's say in mean. So we want to count expectation of this random variable x. X is how much money we will get at the end. X is a random variable because it is not deterministic. It can equal to 1 to 100 to 2. So we can easily show that we will earn 0.5 on $1 plus 0.1 on $100 and 0.4 on $2. Yeah, and we can count the result. It would be 0.5, 10, plus 10 plus 0.8. It's $11 and 30 cents. Okay, so it's not very hard. This is a mean of distribution, mean of random variable. So mu is mean. You can see it is in formulas, and we can show that if we count expectation with of this density, we will get mu exactly. Yeah, by the way, for non-discrete variables, we can count distribution like density on value. Very similar to how we do it just now, but but for discrete variables, instead of integral, we can use summation for all discrete variables x, probability of x on x, and here is an integral. Yeah, sigma is standard deviation. Deviation is another statistics like mean for distribution, but it shows how different variables are. For example, if you can obtain only one variable, so in fact it's not random. There is no randomness, but of course we can say like it's random variable, but it always equal to the same value. So if there's only one value, the standard deviation is 0. And it counts like expectation of random variable x minus mu. It's a mean, yeah, and squared. In fact, it's expectation, yeah, of difference, square of difference between random variable and mean. And it shows how different variables are. So this is sigma. P and E, I think you know these constants. And let's take a look at graphics. We can see different graphics for different sigmas. Yeah, and we see that the value, it's the density function, and we see that the sigma controls the wideness of the graphics. Yeah, by the way, here is not zeros. Here values are very close to zeros. Okay. So the bigger sigma, the more values can be taken with more probability. It's this is what standard deviation shows for distributions. Okay, and to generate different samples, we can use this normal distribution of Gaussian noise and start with it. So we sample a random Gaussian noise and put it to the model input, and the model will generate some image or text or something else. Yeah, so G is neural network, our generator, and X is the output of it. So the pipeline of our generative model is to put a unit Gaussian noise into input generative model and obtain a new variable. And these variables would be from generated distribution. And we have a true data distribution. And we want these distributions to be close. In ideal to be the same, but we want to create a loss that will make them same. So the the closer distributions are, the loss will the loss should decrease. Yeah. I would say that the generative model generates only one sample, not the whole distribution, but the sample is from this distribution. So we want our loss to make these distributions closer. Okay, let's go. In GAN generative adversarial networks, we also have discriminator. It's our simple discriminative model, but now we want it to distinguish fake generated examples and real examples. So in fact, we have two models that are playing a game. Generator should learn how to create fake samples very, very similar to true distribution. And discriminator should learn how to distinguish real examples from fake examples. And in process of training, they become more clever and more clever. And at final, we will obtain two good models, first generator that can generate good fake examples, very similar to real examples, and a discriminator that can distinguish them. And then we will use only generator, of course. We don't need discriminator in most cases. So, in fact, discriminator is a judge, and for it, we want to use something like cross-entropy loss. We have two classes now, real class and fake class, and at its input, it gets one image and should predict if it is real or fake. I will remind you what is cross-entropy loss. You can find a formula here. It's pretty simple, in fact, for two classes. And now what we have? First, we want to create a loss for discriminator. For module D, X is a real class, is a sample from a real class from our data set. Yeah, and we want it to it's like in cross-entropy loss with positive Y. Y is 1. And here we have Z is a Gaussian noise. Then we obtain from generator fake object. And here we predict the class of fake object. And like here, it's a sample with a negative class with Y0 labeled by 0, yeah? So we take it with log 1 minus our prediction probability. And we want to minimize cross-entropy loss, yeah? So discriminator should be very good, and loss should be small. But for generator, we take this loss with minus. Why with minus? Because for discriminator, we want to minimize this loss. But generator should make discriminator make mistakes. So generator wants to obtain big loss. So it's because they're playing a game with discriminator, and generator wants to win. And it wants to discriminator show bad results. That's why we want this loss. In fact, generator wants to maximize this loss. Okay, let's go on. But what should we do now? We have two losses, and the purposes of these losses are opposite, exactly opposite. So we have this generator, we have discriminator. We go for some. We'll go through dataset, obtain batches, calculate loss for discriminator, as I explained before, and optimize only discriminator. Yeah, because first step, only discriminator becomes more clever, and it optimizes himself using cross-entropy loss with like in classic approach. We want to minimize cross-entropy loss. And then we generate Gaussian noise, calculate generator loss, and optimize generator you can see that these are weights of discriminator from here, and these are weights of generator. And now we maximize cross-entropy loss and optimize only generator. So here we make discriminator more clever, optimizing only discriminator. So we should optimize cross-entropy loss. And here we make generator more clever. So we should optimize minus cross-entropy loss, or make cross-entropy loss, or we should maximize cross-entropy loss, because we work only with the generator. So now we have two steps, one for discriminator, one for generator. And I also want to say that here in a second, I'll clear. Here in discriminator loss, we update. Oh, here in generator loss, yeah, this is the same, but with plus. It's like for here. We update only generator, and in this part we don't have any generator, so we don't need it because it's a constant. We optimize only generator weights, and here, and this is a constant considered on these weights, only for generator loss. So for generator loss, we should optimize only this part. That's why we don't need x, a true object. So here, that's why here for generator we don't count data. Yeah, we don't need data. We count on the we sample noise and use only it. Okay, that's all. That's vanilla generative adversarial network. Two models, generator, discriminator. But in fact, it is very hard to train them. If you will run this pipeline, the results will be very, very bad. And there are many tricks to overcome this problem. First is replace logarithm of 1 minus discriminator to minus logarithm of discriminator. In fact, they are very similar because we can show that if d decreases here and here, the result goes in the same direction. And if d increases, let's say, they're very similar, but the right part is more stable. It makes training more stable because it has better gradients. So we should use it. Another trick is make more uncertainty. We should use label smoothing. What is label smoothing? It's a common approach when we have, for example, two labels 0 and 1 for classification task, for example. And in cross-entropy loss, instead of 0 and 1, we should use something like random for 0. We should replace 0 with something random from 0 to 0.2, and should replace 1 to something random from, for example, 0.8 to 1.2. I will show. So 0 goes to something from 0 to 0.2. And 1 goes to something from 0.8 to 1.2. So we say for model that we don't very certain in these labels, and so it would be okay if you will give others. And the model would work better. Label swapping. Sometimes we want to swap labels and make examples incorrect. So we say something like, be robust if you have front data. Another trick is add supervised loss. For example, as we saw at the first slide, second slide, you have data like this. we know that some data is for dogs, some data is for cats, and we want discriminative model to predict dogs and cats. We want to predict real and fake, and also if it is a dog and if it is a cat. This will help discriminative model to learn more about data, and it will be more clever. And use leaky ReLU, because sparse activation functions like ReLU, for example, is bad, and it usually and we usually want to use exactly leaky ReLU. It's important. It would work better. And another trick is to add random noise to feature map to avoid mode collapse. And with this, we will discuss this later when we will discuss what is mode collapse for GANs. Okay, next module is Variational Autoencoder, VAE. Let's briefly talk how it works. On the right, you can see the architecture of the model. We have at the true dataset D, true samples. Then this is the distribution. Yeah, it's very complex. So we don't know how it looks like. First, we map it to prior distribution and obtain Z. In fact, we encode, for example, we have an image, we encode it into a representation from this distribution. And we want this distribution usually to be Gaussian noise with the mean 0 and sigma equals to 1. And from this noise, we want to reconstruct the same element X. So while training, we will obtain X from dataset, encode it, and then decode and then decode back. And it's while training. And while inference, we will sample Z from this distribution and decode it into element from our true distribution. So the architecture is a pipeline. The architecture is like this. We have input true element, then we encode it into element from this distribution. How we will obtain mean of this distribution and sigma of this distribution. So when we will obtain mu and sigma, we will generate sample from Gaussian from a normal distribution with these parameters. Yeah, we can do this easily. For example, Torch, NumPy libraries provide us with provide us these functions to generate, and then we'll decode this noise into an output. Yeah, here you can see our input space. We obtain mu, obtain sigma, so we have some distribution inside latent space. Then we generate from distribution, for example, this one, and decode back. And we want to these input and decoding to be similar. It wouldn't be the same because we have some randomness, but we want them to be similar. Okay, what's the problem? When we want to train the model, we have F is our loss. We can the gradients can flow through decoder, yeah. But then we obtain, but when we have sample Z at the beginning, we have X, our input, we have phi. Our encoder weights, and using them we obtain Z, yeah, because our encoder gives us mean, mu, and sigma, and we sample Z, yeah, using X. We obtain mu and sigma using X, but sampling Z is not a function, and it doesn't have gradients. How we can use, for example, SGD, stochastic gradient descent,
to optimize phi. We can optimize decoder because the decoder is after that. But how to optimize encoder? We can use reparameterization trick. What does it say? We can show that z is a function from epsilon, phi, and x. We know phi and x, we discussed it before, but what is epsilon? It's a noise from normal distribution, from standard normal distribution. Standard is like mean zero and deviation and sigma one. Yeah, epsilon samples from here, and it is easily shown that to sample from this distribution, we can sample epsilon, multiply it on sigma, and add mu to it. So in fact, we can show that our z is a function from epsilon, phi, weights, yeah, and x. That's true. So in this scheme on the right, we can see that z is obtained by epsilon, and now z is a function from phi, x, and epsilon, function, moreover, linear function. So we have gradients for it, and we can count gradients considered on phi and weights of encoder. And now we can use SGD, we can use gradient descent and update gradients. So everything is okay. It's called a reparameterization trick, and it helps to overcome problem that sampling z is not a function and we can't count gradients when we're sampling something. Okay, let's go on. Let's discuss the loss. There are different, there's a good explanation of why we want to use VAE, why we obtain these losses, but we need some maths, and we will skip today these explanations and go to results. In result, we have two losses, reconstruction loss and regularization term. Here is chiral divergence. In fact, it is a metric on two distributions, and it is small when distributions are similar. Yeah. And so, in fact, it shows that these two distributions, the smaller is chiral divergence, the closer are these two distributions. And what are these two distributions, by the way? This is distribution on distribution of our Latin space, our normal distribution, standard normal distribution. And this is distribution of our normal space, but obtained from image. Oh, sorry. This distribution of our Latin of outputs z. So when we have outputs of encoder, this is distribution on it. And we also, of course, want to make distributions outputs of decoders to be similar to Latin space. Yeah, because when we will generate during inference our noise, we would generate from the same distribution that we obtained from outputs of encoder. And reconstruction loss is something like we want the output of the decoder to be the same that our input. It's rather simple. Okay, so these are some maths, and we can show that chiral divergence derived in this formula. These are outputs of encoder, mu and sigma, mean and variance. In fact, we want our encoder to often output not exactly sigma because square of sigma because it should be positive, yeah, our variance. Want to output a logarithm of variance, and then it can be not real. It should be real, so it's easier for our model to learn this. To output not only positive numbers but real numbers. And in formula, we will use here log var, as you can see here, and here log var exp, because, yeah, because log x is variance. Variance is sigma squared. And here is simply a binary cross entropy for reconstruction of x and input of x. I think not very hard. Here you can check the code of VAE, losses, and code decoder. And let's also discuss the losses. Here you can see if we will use only reconstruction loss, you can see that it's for CFR dataset for numbers from 0 to 9 here, drawn with pen, something like this. And you can see that it has good understanding of classes, to sample because they're near. But when we will sample, it's a latent space, that's after training using only reconstruction loss. Here we can see that we have a good understanding of classes because grays, yellows are together, purple is together. This means that because we have reconstruction loss, we generate the same image. But this is a good structure of flattened space. We want it to be normal or Gaussian noise, and Gaussian noise are usually like a circle or something like this, or ellipse. On the second image, where we have only Kyle divergence that wants the distributions to be similar. We see that our distribution of encoder outputs are really similar to Gaussian distribution because it's also like ellipse. But we don't have structure. Our elements are shuffled, so because we don't have reconstruction loss. And using the combination of losses, both of them, we can see that it is similar to Gaussian noise, and also we have structure. So this means that we have a good understanding of structure of our images. Now, because the same colors are together, this means that we have a good understanding of structure of our images. And a good structure of distribution means that it is similar to Gaussian noise. Why it is important to be similar to Gaussian noise? Because during inference, we want to generate samples from this noise. And in first case, for example, we take Gaussian noise like this, generate something like here, and we will get some strange things because we can see that it is out of distribution. And here we will generate from Gaussian noise and generate good numbers. Oh, sorry. And by the way, this is not CIFAR, it's MNIST. My bad. It's numbers from 0 to 9. Okay, so this is the influence. These images show the influence of part of losses on the result. Let's go. Now let's talk about several problems. The problem with generative adversarial network is mode collapse or mode coverage. The problem is that GANs generate very, very similar images. And even if our dataset is very diverse, it would generate samples very, very similar. For example, if we have datasets of humans, GAN can generate, for example, only black-haired man with blue eyes, white teeth, I don't know, something like this. Or in opposite, another GAN can generate only blonde-haired women with green eyes. And it's very hard to make GAN generate diverse images. And this is a problem. It's named mode collapse. In opposite, VAE can generate more diverse images. It has diversity, but the result samples don't have high quality. It's usually blurred, and this is a problem. First, let's talk about why these problems occur. In fact, let's draw, as we showed at the beginning with dogs and cats, in distribution, there can be several classes. So in fact, objects of the same class, let's say they are near to each other. That's usually true. And that's why true distribution usually have several modes. What does it mean? That here is density big, here is density big. Here's density large, and here density large. And between them, there is a space where density is low. So in fact, it's like you can remember algorithm for clusterization when similar objects are together and there are several clusters. The same is here, the same in real data. There's a cluster for cats, for dogs, for human, the cluster for men, for women, for blue-eyed people, for green-eyed people. There are different clusters. But then we want to map this distribution to a normal distribution with only one mode. Yeah, as we saw before, Gaussian noise. There is only one mode around its mean, and here probabilities are close to 0. And we want to map this distribution to this distribution. And what's the problem? The problem is we can't map both. And we have two models, GANs and VAEs. GANs, how GANs do map this true distribution to normal distribution? It tries to find a good place for this distribution with high probabilities. For example, it says that let's take latent space here, and thus we will generate only cats. Yeah. Or in another training, we will map Gaussian distribution here, and it will generate only dogs. Yeah, so it tries to maximize probabilities of its generations, in fact. And here they're big and it's good. And this is mode collapse because we take only one mode. That's why mode collapse occurs. For VAEs, it tries to make true distribution similar to Gaussian distribution. And that's why it tries to use both modes and put them into one normal distribution. But here's a problem. When we will generate samples, we can generate something here in the middle of them and with low density. And thus we will obtain some blurred images with the low resolution and so on. Not very good images. And this is a problem with quality. In result, GANs and VAE tries to map distributions in different ways. First, tries to maximize probabilities and GAN, and so that's why it has mode collapse. And VAE tries to put both modes into one. And thus it can generate blurred images. And these are two problems that can be overcome. Okay, maybe can't is a very strong word. For different data sets, there is a different situation. But as I said, we should add random noise to feature map, as I said, to avoid mode collapse. How it will help? When generator trains to generate samples from the same mode, we add noise, and it could jump to another mode and generate sample from there because of noise. And this sometimes help to overcome the problem of mode collapse with some success. Right. Yeah, and you can see here that there are diffusion models that we will talk later about that generate high quality samples and solve the problem of mod coverage or diversity, mod collapse. But they don't have fast sampling because GANs and VAEs sample fast. They need only one forward propagation through model, for GANs through generator, for VAEs through decoder. But diffusion models need usually 1,000 steps to generate one sample. But they do it with high quality and without mod collapse. And so with good diversity, but very slow. There are some works that try to increase the speed of diffusion models, but it's another story. So for today, we had the GANs and VAEs, generators that generate in good images in good quality. Yeah, and that's all. Thank you. I will give you a homework based on GANs and VAEs, where you would implement them for simple cases, and you will there you will find details about implementations. By the way, there's good implementation of VAE from which I took loss function, and there are also many implementations of GANs. There are many different GANs using different ideas to increase the quality of the model. Also, there are different VAEs. You can read some information from the internet. You can solve the net for it. Yeah, thank you.